Hello, this is Math Jazz from Almost Cool, and today we are going to be talking about injections and cardinality. Um, so we already talked about how the definition of cardinality depends on our definition of bijection. That is to say, two sets have the same cardinality if and only if they have a bijection between them. There might be many bijections between them, but there has to be at least one to have um, the same cardinality between two sets. Well, now we're going to talk about what we mean by having a bijection. Sorry, what we mean by having one set have a greater cardinality than the other. Okay, and so the definition we have here is if A and B. A has a smaller cardinality than B if there is an injective function from A to B. And we say that A is strictly smaller. We say the cardinality is strictly smaller if there is an injection from A to B, but not a bijection from A to B. Okay, so a lot of the proofs today will be dealing with that. So we have an example here. We have a set with 3 elements and a set with 4 elements. And we're going to prove that they are of differing cardinalities. So, well, it's pretty clear to see, and this example is not supposed to be hard. That we can send each element of S to a different element of T, so we can form an injection. Say 1 to 2, 3 to 4, 5 to 6, like that. So S is smaller than or equal to T in number of elements, in cardinality. But T is not able to be mapped injectively to S. Let's say 1 goes to 2, 4 goes to 3, 6 goes to 5. There are no free elements left in S, and 8 would have to double up and hit something that's already been hit. I'm wondering, is there trouble in the live stream right now? No, we're going okay. So that's our example here. Looks like we have another example. The relationship between the sets 2n and n. Well, we can create a bijection. It's just everything in 2n gets mapped to n by cutting it in half. Yeah, so this is an example of a strict inequality between cardinalities. This is an example of equality, so a non-example of one set being larger than the other. And then number 3, what's the relation between sets n and r? The inclusion map is injection, so we get n is less than or equal to r in cardinality. Oh, so apparently the last section we proved that r was uncountable. So that's how we get a strict inequality between these. This is what we mean when we say that there are more real numbers than counting numbers. There are more real numbers than natural numbers. There are more decimals between 0 and 1 than there are counting numbers from 1 to infinity. Saying anything of that kind of flavor is what we mean. That we mean this by that. So there is an injection from n to r, with no bijection between them. Okay. Well, let's see. Oh, we're talking about power sets. Okay. So we're going to prove that the power set of a set always has a greater cardinality than your original set. Now, here's our theorem. If S is a set, then the cardinality of S is less than the cardinality of the power set of S. So let us walk through this proof. This is probably a pretty tough proof for a student to go through. So we'll walk through the steps. Okay. We have to pick an arbitrary set because we're making a statement about arbitrary sets. So we pick an arbitrary set, and we're going to first build an injection from S to P. That'll give us that the cardinality of S is less than or equal to the power set of S. Well, the easy injection is exactly this. Our function f goes from S to the power set of S by f of S equals the set containing S. If we've forgotten what the power set is, the power set is the set that contains all subsets of whatever you're taking the power set of. So let's look at that on our grid, make sure we remember what power set is. So if we have a set, we have a set S, let's say that that's equal to, we'll make a small one so it's easy to work with. 3 elements is pretty small. Here's a set S. Here's our example of a power set. So the power set of S is equal to all subsets of S. So the empty set is always a subset of every set. And then we have the set containing the first element, the set containing the second element, the set containing the third element, the set containing the first and second element, the set containing the first and third element, the set containing the second and third element, and every set is a subset of itself, so we get back S as well. So 1, 2, 3, 4, 5, 6, 7, 8 elements in the power set. And in general, if the cardinality of a set is some number n, then then the cardinality of the power set is going to equal 2 to the n. Okay, so these power sets get big fast. So let's get back to our book. We'll look through this proof and make sure we understand it. Okay, so the first thing to do to prove that S has a strictly smaller cardinality than its power set is you have to prove that there exists an injection from S to the power set. We define that by f of S equals the set containing S. This is obviously injective because the only way for us to get the same outputs for our function is, well, the set containing, oh, here's our proof. If f of A equals f of B, then the set containing A equals the set containing B. If two sets are equal to each other, then they have the same elements in them. Since each of these sets only has one element, then those two elements must be, in fact, the same element. Okay, so that proves our injection. That gives us a weak inequality. We get less than or equal to, but we're going to prove strictly less than right now. And this is the part of the proof that gets complicated. Okay, so I want to walk you guys through this. So we have to prove no bijection exists. So we're going to assume that we have, we're going to take an arbitrary function and we're going to show that it can't be a bijection. Okay, we're going to define this thing called the Barber set. Okay, now let's take a look at what the Barber set is. So our Barber set is the set of all, oh, that was our background. There you go. Okay. I'm gonna make the brush a little bit thicker for you guys. So we have the Barber set of a set S is equal to set of all objects X in S. I guess we need a function defined first. Let's do that. Okay, so let's say we have f is a function from a set S to its power set. Okay? So that means it takes in elements of S and spits out subsets of S. Okay? Then the Barber set of this set and this function is equal to set of all elements X in S such that f of X contains does not contain. And let's write in symbols. X is not in f of X. There we go. And the reason it's called the Barber set is because typically barbers don't cut their own hair. And that sounds kind of like a strange thing to say in relation to a college level math class. But the idea is that since a barber doesn't cut his own hair, he has to go somewhere else to get his hair cut. So these are all of these X's in the Barber set are all of the X's that are not in their own image. They're in the image of some other elements. They're in the some other element's image. They're not in their own. So we think of that as like how a barber doesn't cut their own hair. A barber hires a different barber to cut their hair. These elements aren't in their own image under F. They have to hire some other element and be in that other element's image. It's kind of funny, but that's the reasoning why this is called a Barber set. Okay, so anyway, the Barber set is the set of all elements that are not in their own image. Okay, now the Barber set might be empty. Remember, in the first part of the proof, we defined a function f going from S to the power set of S by f of X equals the set containing X. If this is our function, then the Barber set of F is going to be the empty set, because every element X, its image is going to contain it. But this is still a set. Even though it's an empty set, it's still a set. Now, let's create, say, our function. Let's create another function. We're just playing around with this object a little bit to figure out how it works, how the Barber set works, so that we can feel comfortable with the proof. So here's our set S. We're going to define a function from S to the power set by, let's say, g of 1 equals 2, the set containing 2. Remember, the objects are power sets here. How about 2 equals the set containing 1 and 3, and g of 3 equals the set containing 2. Okay, this is a perfectly valid function from S to the power set of S. It takes in objects of S, spits out objects of the power set of S. So, what would the Barber set of G equal? Okay, well, is 1 in the Barber set? Yes, because here's 1, here's the image of 1. 1 is not an element of that, so 1 is in the Barber set. Is 2 in the Barber set? Yes, because 2 gets sent to something that doesn't contain 2. Is 3 in the Barber set? Yeah, because the image of 3 is the set containing 2. 2 is not 3. 3 is not in the set. So this happens to have the Barber set of G equaling all of S. So here's one example. This choice of function gave us the Barber set's empty. This choice, this choice of F, this one gave us the Barber set was empty. This choice of G gave us the Barber set that was the entire original space, the entire original set S. So and if you played with a little more, you can create any subset of S as the Barber set. If I wanted to have the set 2, 3 as the Barber set, I could do it like so. And this will be the last example of the Barber set before we this will be the last example of the Barber set before we move on to the proof again. Okay, so let's say that we have h of x equals, well, let's say h is a function from s to the power set of s by h of 1 equals 1, 2, h of 2 equals 1, 3, and h of 3 equals 1, 2. Okay? That means the Barber set of h is going to equal, well, 1 got mapped to something that 1 is in, so 1 is not in the set. 2 gets mapped to something that 2 is not in, so 2 is in the set. 3 gets mapped to something 3 is not in, so 3 is in the set. There we go. So this is now our example of something that our Barber set is not empty, but it's also not everything. Okay, so now that we've completed all of these examples, let's go back to the proof that we have and see what we can deduce from it. Okay, so let's see. We've defined the Barber set and we feel comfortable with it. This is a subset of S. Yes, no matter what our function is, B will be, the Barber set will be a set. And it will be in the power set as well. So we need to show that B is never in the image of G. Okay? So we have some set G that goes from S to the power set. So case 1, if S is in G of S, then S is not in B, so G of S is not B. Right? I mean, B was all the things that don't get mapped to themselves. So if S is mapped to itself, then, or mapped to something that contains it. So that means that G of S can't be B. Okay, what if S is not in G of S? Well, then S is an element of B. But G of S never maps to a set that contains, okay, so let's see, sorry, case 2. S does not exist in G of S. Then S is in B, because the image of S does not contain S. That's the definition of being in B. Okay? Okay. So why would that mean that G of S is not equal to B? Oh, well that's easy. Since S is not in G of S and S is in B, well, S in B means that G of S can't be B, because you can't both be in a set and not in the set. If G of S equals B, then S is not in G of S, which is B, so S is not in B. And S is in B, which is G of S, so S is in G of S. But that's a contradiction. So that means that if these two things are true, then G of S can't equal B. So that means that no matter what, B is not going to be in the image of G. So B doesn't get hit by S for any S in S. For any little S in S. Yep. Okay, so that gives us our proof that there exists some element in the power set that is not in the image G. So no matter what our function is, since G was chosen arbitrarily, G is not surjective, so G is not bijective, so there is no bijection between S and its power set. Okay, so that's cool. Okay. What's this? Ah. So is that an F? F of S is the set of all functions from S to 0, 1. Yeah, this is obviously going to have the same cardinality because you just say, well, the function from the power set to F goes 0. Basically, for any element of S, the its coordinate in F of S is going to be 0 for an element of the power set if it's in that element, and 1 if it's not, or switch it around, vice versa, however you want. Let's see, this is, let's see, yeah, so a chi function is going to be 0 if the element's not in it, and 1 if it is. Which is what we said. This proof is not so hard. Let's see, corollary 31.7. The power set of the naturals equals, or is the same cardinality as f of the naturals and is uncountable. So, this is the number of strings of zeros and ones, infinite strings of zeros and ones. That's uncountable. Since there's a 1-to-1 correlation between these, the power set of n is also going to be uncountable. Yes, see? So, f of n is going to be the same as this infinite product of zeros and ones. So, which apparently you proved is uncountable. Okay, let's get into exercises now. Let's see. Answer each of the following true or false problems, proving your answer. Every uncountable set has the same cardinality as 0, 1. That is false. Oh, and so the proof of this is actually pretty easy because we know that the power set always has greater cardinality than the original set. So that means that the cardinality of 0, or the cardinality of this set 0 to 1 is less than the cardinality of the power set from 0 to 1, or the power set of the interval from 0 to 1. So the answer to this is no, and there's our example. Let's see, let A and B be sets. If A is contained in B, then the cardinality of A is less than or equal to the cardinality of B. Yes. The proof is, let your injection be the identity map on A. That will be, the identity map is always injective. Have it go from A to B. There's your injection from A to B. And that proves this. That's the definition of that statement. For sets A and B, if A is a proper subset of B, then the cardinality of A is strictly less than B. Well, we know that's not true because we proved up here, let's see, we proved that the cardinality of the evens is the same as the cardinality of the naturals. So, and the evens are a proper subset of the naturals. So, and by that I mean even naturals, not even integers. So that's our example for that. So that shows this is false. Given sets A, B, and C, if A is contained in B, contained in C, and both A and C are countably infinite, then B is countably infinite. Yeah, that's true. We know that if we have an infinite subset of a countably infinite set, then it's countably infinite. So if C is countably infinite, A being countably infinite means A is infinite. So, oh, yes. A being countably infinite means A is infinite. Containing an infinite set means you're infinite. So B is infinite. B is infinite subset of a countably infinite set, so therefore B is a countably infinite set. There we go. That uses theorems from 29, I think, or 30. It's somewhere in the book, but it's the two statements you need are containing an infinite set makes you infinite, and being infinite and contained in a countably infinite set implies you're countably infinite. So A is countably infinite, so it is infinite. So that means B is also infinite because it contains an infinite set. C is countably infinite. B is contained in it and countable and infinite, so therefore it is countably infinite. Okay. No subset of R has smaller cardinality. No subset of R has smaller cardinality. Smaller than what? Smaller than R? I don't know if that's a meaningful statement there. No subset of R has smaller cardinality than R. Well, like, just grab the empty set. It has 0 cardinality. It's a subset of R. I'm going to say this is false. I'm sure that they mean smaller cardinality than R. For sets S and T, if S has smaller cardinality than T, and S is finite, then T is infinite. Well, like cardinality 1 and cardinality 2. So that's false. Like set containing 1 element, set containing 2 elements. 2 is finite, or is it T is finite, 2 is finite. But it still is strictly greater cardinality than S. See, for sets S and T, if S has smaller cardinality than T, and S is countable, then T is uncountable. Well, yes, because countable means it has cardinality of the naturals or some subset of the naturals. And if you're larger cardinality than that, then you're not the cardinality of the naturals or something smaller than the naturals. Oh, but it doesn't say countably infinite. Okay, so scratch that. We're gonna restart. Let S be like the set containing 1 element, and then T is the naturals. S is countable. T is also countable, but T is bigger than S. Not countably infinite, just countable. For sets S and T, if S is strictly less than T, and S is countably infinite, then T is uncountable. This is true because if T were countably infinite, then it would be the same cardinality as S. If T were finite, then it wouldn't be smaller. Sorry, then S would not be smaller than it. It would be S would have bigger cardinality than it. So T can't be countably infinite. T can't be finite. That leaves the only possibility is T is uncountable. Okay, for any set S, there exists another set T where S is smaller cardinality than T. Yes, the power set of S has greater cardinality than T, strictly greater than. Sorry. The power set of S has strictly greater cardinality than S. So, for any set S, just let T be the power set of S. That's true. Okay. Let's see. Let S be a set of 5 element. Okay, I've been saying the set with 1 element, the set with 2 elements. Technically, it's a set with 5 elements here. Because if I swapped all of these for 1, 2, 3, 4, 5, it would have the same number of elements, but it wouldn't be the same set. So let S be a set with 5 elements. G go from S to the power set be defined by this rule. List the elements of the Barber set. Okay, so does A go to a set containing A? No, so A's in the set. And looks like B's in the set. C is not in the set because C goes to a set that contains C. So A and B, but not C. D goes to the Barber set. E does not. So A, B, D. Those are the 3 elements in the Barber set. And then why is it not in the image of G? Well, because we proved it up here in this theorem. No, not this theorem. this theorem. In 31.5, we proved that no b is never in the image of a function from a set to its power set. So you can say that in your answer. Just say, why is the Barber set not in the image of G? Because of part of the proof of theorem, whatever the theorem was, that the power set of S has a strictly greater cardinality than the set S does. Okay. Exercise 31.3. Find a set with cardinality bigger than R. Okay, power set of R. Then find a set with cardinality bigger than that. Power set of the power set of R. Okay, that was two of those. And you can just cite that the theorem that we talked about. Cardinality of the power set's bigger than the cardinality of set. That proves it. Okay. Exercise 31.4. Pigeonhole principle says that for finite sets A and B, cardinality of A equals cardinality of B, and F is a function. F is injective if and only if surjective proves this fails for infinite sets by proving the following. Find an infinite set S and a function S to S that's injective but not surjective. Find an infinite set S and a function S to S that is surjective but not injective. Okay, so let us pull up our scratch paper for this. This one looks fun. Okay. So scroll a little too far. Okay, so we just need to find a function from S to S that is not injective. I might be switching the order of these. And a function from S to S not surjective. Oh wait, we want this one to be surjective but not injective, and this one to be injective but not surjective. Right? Is that what we want? Let's go back and look. First one is injective, not surjective. Second one is surjective, not injective. Okay, so let's do injective, not surjective first. That was what was asked for first. So let's say F goes from the naturals to the naturals by f of x equals x plus 1. Let's see. So that means that let's prove injective. If f of x equals f of y, then x plus 1 equals y plus 1, which means that x equals y. So that is injective. Let's prove not surjective. Well, no natural value of x gives f of x equal to 0. Why is that? Well, let's see. X, like f of x equals x plus 1 equals 0 implies x equals -1, and that's not a natural number. So that proves not surjective. Okay. Now we want surjective but not injective. Okay. Let's see. How about f of x equals x minus 1 for x greater than 1 and 1 for x equal to 1. Okay, so obviously f of 2 equals 2 minus 1 equals 1, and f of 1 equals 1. So this is not injective. Why is it not surjective? Scroll over a bit. sorry, why is this surjective? Well, let y be a natural number. Let x equal y plus 1. Then f of x equals x minus 1. Well, because if y is a natural number, then y plus 1 is, so y is at least 1. 1 plus 1 is at least 2. So x is going to be at least 2. So that means that f of x is going to be in the first definition. Going to be 2 is, x is always going to be 2 or greater, so it's always going to be greater than 1. So it's going to use this top part of the definition here, not the bottom part. So f of x equals x minus 1, because x is always greater than or equal to 2. But that's equal to y plus 1 minus 1, which is equal to y. Hey, look, we found, for any natural number, we found how to find an x that gives us f of x equals that number. Okay. So this one is in fact surjective, but not injective. So that gives us the answers to this problem here. Okay, so 31.5. Let's see. Let A and B be sets where F is a bijection. Define a new map from the power set of A to the power set of B by this rule. Prove that G is a bijection. Conclude if A has the same cardinality of B as B, then the power set of A has the same cardinality as the power set of B. Okay, so we want to prove that this function is a bijection. Okay, so let's go back to our paper. So to prove that we have a bijection, so what we know is that F goes from A to B is a bijection. And we're defining G goes from the power set of A to the power set of B by G of S, where S is some subset of A, equals the set that contains F of little s such that S is an element of big S. So let's prove injective. Okay, so if G of X equals G of Y, then, well, this is going to be a set F of S such that S is in S equals, roll a little right, F of T such that T is in T for some S and T subsets of A. Well, for these sets to be equal, that means that for every S in S, there exists T in T such that F of S equals F of T. Why does that have to be true? Well, if these are equal sets, that means that anything that's in one set is in the other. Okay, so without any loss of generality, we'll just pick elements from this set and match them up with ones in that set. We know that we could reverse the order, pick elements from this set and find their corresponding elements here. And that would be totally fine. So we'll actually mark that here. So, what does that mean? Well, f is bijective, so if f of s equals f of t, so that means that s equals t. For every s, we find a t such that f of s equals f of t, but that means that s equals t, so that means that big S equals big T. Since every element of big S, there's a corresponding element of T that is equal to it. Well, what does that mean? That means that well, S and T are subsets of A, so they're elements of the power set A. So this proves G is injective. Okay. I guess I switched variable names through here, so we will fix that. Doesn't particularly matter, so long as you're consistent. There we go. Big S. My brush not work. Big S. There we go. Okay, big S equals big T. Then for every element, little s in S, f of s, this set equals that set, so we can build this correspondence. So G is injective. Let's prove surjective now. Suppose big T is an element of the power set of B. Then T equals some number of elements. We'll have T1, T2, T3, ... Now this doesn't mean that there are countably many of them or finitely many of them. It just means that there's some collection of elements. So define S to equal... Actually, it's probably better to just not bother naming these. So we're just going to get rid of all of these. Then define S to be the set. We're going to have F inverse of T such that T is an element of big T. We could do this because we know F is bijective, so F is invertible. So all we do is we take every element in T, we invert it, and we create a set of all of those things. What does that do? Well, G of S is equal to the set F of S such that S is in S, right? But that's going to be equal to the set F of F inverse of T for all T in T. But what's that equal to? Well, F and F inverse cancel because F is bijective and therefore invertible, and so it cancels with its inverse. We get T such that T is in T. What is the set of elements T that are taken from the set big T? Well, that's going to be just the set big T. Hey, look, it's surjective because we took an arbitrary element of the codomain and we found an element that has its image equal to it. An element of the domain that has its image equal to it. Great. So that's not too bad. So let's go back to, oh, did we not switch cameras? Let's see. It looks like you guys can see this. Okay, so let's just do, here's the proof of injective up here. And here's the proof of surjective down here. You guys can see those. Okay, let's switch back to our book. Okay, so the next exercise, define a function f from R to the power set of q by this rule, prove that f is injective. Okay. From R to the power set of q by this rule. Okay. Let's pull up paper. So f goes from R to the power set of q by f of x equals the set y such that y is less than or equal to. Is it less than or equal to? Let's check the book again. Less than or equal to x. Oops. I want to prove that this is injective. So, suppose f of x equals f of y. Then set of all elements t such that t is less than or equal to x is equal to the set of all s such that s is less than or equal to y. Well, we know that between every two real numbers there is a rational number by a proof from chapter 11. So if x is not equal to y, then y is greater than x, or x is greater than y. By symmetry, we'll just take y is greater than x. The proof either way is the same. Okay, so because if x is bigger than y, just switch the names of them. Okay, so y greater than x implies that there exists q that is between, there exists q such that x is less than q is less than y. Well, what does that mean? That means that q is in f of y and q is not in f of x. So f of x is not equal f of y. That's a contradiction. Well, what does it mean to have a contradiction? Like, remember, we supposed f equaled y. F of x equals f of y. we got this. This is a contradiction. Therefore, the last thing we assumed must be false. So crawling back through here, we see where is the last thing we assumed. That. If x is not y. Okay. So that statement is false because that's the last thing we assumed, and we did a proof by contradiction. So x equals y. That means that if f of x equals f of y, then x equals y. That's the definition of injective. Okay, so back to the book. We take a look. Part B, it says prove or conclude that the cardinality of R is less than or equal to the cardinality of the power set of N. Well, we gave an injection. Definition of smaller cardinality was if there's an injection. So that's just a definition. Okay. And the last problem from this section, looks like we're going a little bit faster than through this section than we usually get through these sections. Let A and B be non-empty sets. Prove that there exists an injection from A to B if and only if there exists a surjection from B to A. Okay, so let us prove this. Injection from A to B if and only if there's a surjection from B to A. Okay. So there exists F from A to B injective if and only if there exists G from B to A surjective. Okay, so the forward direction is there exists an injection. We're going to prove there is a surjection. Let F from A to B be injective. Okay, so define G from B to A such that G of B equals A where F of A equals B and yeah. We need to define one thing before we get to this point. So A is not empty, so pick A in A. We know we can do that because we know A is non-empty. Now we're going to define G from B to A as follows. If B is in the image of A, then there exists X in A such that F of X equals B. Let G of B equal X. If B is not in the image of A, this is the image of A under G. then let g of b equal a. Well, what does that do? Graphically, it looks something like this. So we have, here's a, here's b. We know that there is an injective function going like so. There's little a, little b. Oh, that's not little b. Little a, little c, little x, little f. Not little f, we use f. Little y. And these all get mapped over like so. But there might be points in b that aren't in a. So what we do is we're going to define, this is our function f, and we're just going to say, for every element here that got hit by something in a, we're just going to go backwards along the line. So g is going to be like so. This goes to here, this goes to here, this goes to here, this goes to here. So all of these elements that were hit by something in a, we're just pulling them back to a. Here's our function g. What about all the things that weren't hit by elements in a, that f didn't reach, the image of f didn't contain? Oh, well, just pick an arbitrary element here. We'll just go send all of these to that element too. There you go. So everything that didn't get hit gets sent to some element A. How do we know this is surjective? Well, suppose y is an element of A. Let x equal f of A. Sorry, f of y. How do we know that there's such an x? Well, because f is a function, and therefore it's defined on every y in A. So, what happens when we do g of x? We get g of x equal f of y. G of f of x, which is, well, sorry, f of y. Well, what does that give us? We start off with some y over here. Here's f of y, and then back to y again. Done. Okay, so that proves surjectivity. That's one direction. So the other direction is, let's say we have a g that's surjective, prove that we can find an f that's injective. So we have the reverse direction. G from B to A is surjective. Okay. So what that means is, for every A in A, let f of A be some element of B such that g of f of A equals A. How do we know this exists? Well, since g is surjective, we know that every element of A gets hit by at least one thing from B. You just pick one of them. You might, if you only have one of them, that's great. That's the one that you pick. If you have more than one of them, well, just pick one of them and it doesn't matter which one you pick. So, why is this thing going to be injective? Well, suppose f of x equals f of y. Then, well, what does that mean? If f of x equals f of y, then we know that g of f of x equals g of f of y. But what's G defined as? Well, F is defined as the thing that inverts G. So that means that this is going to be, G of f of a equals a, so G of f of x equals x. But G of f of y is also equal to y, because we chose G and f so that they canceled each other. So that means that we're injective. Okay, so, and that's all of the problems from this section. So, next week I will be at a research conference. I will do some videos, but they will not happen at their usual Tuesday and Thursday 2 o'clock time. So, you should probably pay attention to your emails, my students, so that you can know when I find time to do these. I'll do 2 hours next week. And also, you should subscribe so that you get notifications when I get online. Okay, so see you all next week at a to be determined time, and also good luck with the end of the semester. We only have, I think, 2 weeks left, so good luck with that, and goodbye.